Hello students, welcome to EPG Pathshala. I am Dr. P.K. Aluwalia from Physics Department, Himachal Pradesh University, Shimla. Today we are going to discuss about the module Classical System of Interacting Particles Part 2, which includes Myers cluster expansion and derivation of virial coefficients from paper Statistical Mechanics. This module on Classical System of Interacting Particles Part 2 has been developed for postgraduate level as per the following subtopics: expansion of van der Waals equation in number density, Myers linked cluster expansion which includes Meyer function and series expansion of configuration partition function, notion of n particle graph in L cluster, constructing the function S ML, counting the terms in the expansion, connecting virial expansion of equation of state and cluster expansion, calculation of virial coefficients of the second order B2 and the third order B3, limitations of cluster expansion. After studying this module, you shall be able to appreciate the need to carry forward a systematic study of real gases, also known as imperfect gases, and know how to get realistic equations of state for these. You will be able to understand how the interaction potential between the particles can be introduced, and equation of state of an imperfect gas can be written as a series perturbation expansion in terms of powers of number density n upon v, called virial expansion, containing virial coefficients which represent microscopic interaction between the particles. You will be able to depict various terms in Myers linked cluster expansion graphically as n particle graphs with L clusters linked with L cluster integrals. You will be able to connect virial expansion of equation of state and cluster expansion of equation of state. You will be able to use virial equation of state to derive van der Waals equation of state. You will also be able to obtain general expressions for second and third virial coefficients for a typical interatomic potential. You will be able to appreciate the limitations of the Myers linked cluster expansion approach in the light of high density systems. So students, in the last module, we looked at the need for going beyond ideal gas model and discussed in detail the types of model potentials proposed to include interactions among the gas particles. We also studied the phenomenological model of a real gas proposed by van der Waals, leading to famous van der Waals equation of state, providing a basis for gas-liquid coexistence phenomenon. However, van der Waals equation is the simplest of real gas equations of state. Later, Thiessen and Kremling-Onnes carried the study forward, providing a very strong theoretical background, and proposed the virial equation of state as an infinite power series in terms of number density small n is equal to number of particles divided by the volume occupied by the particles of the gas, namely P upon kBT is equal to n plus second order virial coefficient B2, which is a function of T multiplied by n square, plus third order virial coefficient, which is a function of temperature multiplied by n cube, plus so on. The quantities B2T, B3T are called second, third and so on virial coefficient respectively, which depend only on temperature and are independent of pressure and density. In this module, we see how statistical mechanics can be used to evaluate virial coefficients systematically by a method proposed by Meyer called cluster expansion method, which is indeed a perturbation expansion approach starting from the classical partition function of an n-particle interacting gas. The first term of this expansion provides the ideal gas result, and subsequent terms give corrections because of interparticle interaction. In fact, we will be able to see how each virial coefficients relate to interparticle interaction. We will find that the jth virial coefficient in fact corresponds to inclusion of j particle interactions in a given volume V. Let us begin with a digression in which we do an expansion of van der Waals equation in number density. We can see that van der Waals equation of state can also be written in powers of number density as pressure P is equal to n times Boltzmann constant multiplied by T divided by V minus Bn minus A times n square upon V square is equal to small n, which is number density, times Boltzmann constant into T divided by 1 minus B times small n, which is number density, minus A times n square is equal to small n times kBT multiplied by 1 plus B minus A into small n plus B times small n raised to power 2 divided by 2 plus so on. That is, P upon kBT is equal to n plus B minus A times n square plus B square upon 2 times n cube plus so on. However, it remains phenomenological in its basis, and we need to approach it from microscopic point of view, starting from partition function of the system with the knowledge of the Hamiltonian of the interacting system of particles at hand. This is what we will do in the following: canonical partition function and configurational integral of an n-particle interacting system. We have a system of classical n-particle interacting systems confined to a volume V and temperature T. The Hamiltonian of such a system is given by H is equal to summation over I pi square upon 2m plus u as a function of r1, r2, r3 and rn, the position vectors of particle 1, 2, 3 and so on up to n, where pi's are momentum coordinates and ri's are the position coordinates of the ith particle. U is the potential energy of the system. It is further assumed that the particles of the gas interact in pairs only, and all many-body interactions are neglected. That is, U is a sum of pairwise interaction potential. That is, the pair potential between any pair of particles I and j, small uij is equal to small u as a function of modulus of rj minus ri, which is central and therefore depends only on their separation rij, which is equal to modulus of rj minus ri, such that capital U is equal to sum over I such that I is less than j, small u ij, where summation is over n times n minus 1 upon 2 pairs of particles among n particles of the system. Summation over I less than j avoids double counting of the pairs. The canonical partition function of such a system can be written as z as a function of number of particles, volume V and temperature T is equal to 1 upon n factorial h raised to power 3n integral of e raised to power minus beta summation over I pi square upon 2m minus beta summation over I less than j uij d3np d3nr is equal to 1 upon n factorial h raised to power 3n integral of e raised to power minus beta summation over I pi square upon 2m d3np multiplied by integral of e raised to power minus beta summation over I less than j small uij d3nr, which is made up of two parts. First part is dependent only on momenta of the particles and second part only on position coordinates of the particles involving interaction potential energy. Integration over momenta is straightforward and gives 2 pi m k b t raised to power 3n by 2, such that 6 can be written as z as a function of n, v and t is equal to 1 upon n factorial lambda raised to power 3n integral of e raised to power minus beta summation over I less than j uij d3 n r is equal to 1 upon n factorial lambda raised to power 3n integral over product over I less than j e raised to power minus beta uij d3 n r is equal to 1 upon n factorial lambda raised to power 3n q as a function of n, v and t, where lambda is the mean thermal wavelength of the particles and q as a function of n, v and t, which is equal to integral over a product of I less than j e raised to power minus beta uij d raised to power 3n r is configurational integral of the system. For an ideal gas, seventh yields Z0 as a function of n, v and t is equal to 1 upon n factorial lambda raised to power 3n integral over d3 n r is equal to v raised to power n factorial lambda raised to power 3n. Meyer's linked cluster expansion. Meyer function and series expansion of configuration partition function. To go into details of the interacting case, let us analyze the function e raised to power minus beta uij and define an auxiliary function also known as Meyer function fij is equal to e raised to power minus beta uij minus 1. These two functions are plotted in figure 1 below. It is obvious from the figure that function uij corresponds to a strong repulsive force at short distances, attractive force at intermediate distances, and falling to 0 at large distances. The Meyer function is identically equal to 0 in the absence of interaction, that is uij is equal to 0. However, in the presence of interaction, it is non-zero, but at sufficiently large temperature, it is much smaller than 1. From figure 1, it is clear that Fij is bounded at all values of Rij. However, it becomes negligibly small beyond the effective range R0 of the potential and is most suitable for series expansion. Let us rewrite the configurational integral in 7th as q as a function of n, v and t is equal to integral over product over I less than j of e raised to power minus beta uij d raised to power 3n r is equal to integral over product over I less than j multiplied by e raised to power minus beta uij minus 1 plus 1 d raised to power 3n r, which is equal to integral over product over I less than j multiplied by Fij plus 1 d3n r, or qnvt is equal to integral product over I less than j Fij plus 1 d3n r is equal to integral over product I less than j Fij plus 1 d cube r1, d cube r2, d cube r3 and so on up to d cube rn. Integrand in 10 is made up of a product of n minus 1 into n divided by 2 terms, one for each distinct pair of particles, which can be expanded as q as a function of n, v and t is equal to a multidimensional integral from d cube r1 to d cube rn over 1 plus f12 plus f13 plus f14 plus so on plus f12 into f13 plus f12 into f14 plus so on, or qnv2 is equal to a multidimensional integral over 1 plus summation over I less than j Fij plus summation over I less than j and summation over k less than L Fij Fkl plus so on d cube r1, d cube r2, d cube r3 and so on up to d cube rn. In writing the configurational integral in terms of Fij, we notice that integrand never goes to infinity, and whenever particles are not close enough, Fij goes to 0. Also, since it is a function of modulus of Rj minus Ri, variables may be changed to Ri and Rij, facilitating integration of the type double integral over Fij d cube Ri d cube Rj as integral over d cube Ri integral over Fij d cube Rij is equal to V times integral over Fij d cube Rij. If we assume interparticle potential to be central, integral Fij d cube Rij can be written as integral Fij 4 pi Rij square drij. With the knowledge of the fact that Fij goes to 0 when the ith and the jth particles are far apart, the limits of integration can be extended from 0 to infinity. Furthermore, as a specific example, let us consider the case of a 3-particle system. Then, Q as a function of 3 particles, volume and temperature will be equal to 3-dimensional integral over 1 plus F12 plus F13 plus F23 plus F12 F13 plus F12 F23 plus F13 F23 plus F12 F23 F13 d cube R1 d cube R2 d cube R3, which can be seen as made up of 3 parts. Q1 as a function of 3 particles, volume V and temperature T, plus Q2 as a function of 3 particles, volume V and temperature T, and Q3 as a function of 3 particles, volume V and temperature T, where Q1 is equal to a triple integral over R1, R2 and R3, which is equal to V raised to power 3. Q2 is equal to a triple integral over the sum F12 plus F13 plus F23. Q3 is equal to a triple integral over F12 into F13 plus F12 into F23 plus F13 into F23 plus F12 into F23 into F13. Notion of n-particle graph and L cluster. There is an interesting graphical way to represent the terms in 15 in an n-particle configurational integral as n-particle graphs, leading to the notion of clustering, which facilitates the calculation of n-particle configurational partition function. We describe this below by an example for a 3 particles. Figure 2 shows graphically the term Q1 3Vt with all the 3 particles free, not forming any Fij bond. Figure 3 shown here graphically represents the term Q2 with 3 graphs with single Fij bond, each corresponding to F12, F13 and F23 bond. Figure 4 graphically represents the term Q3 with 3 graphs with 2 Fij bonds, each corresponding to F12 into F13, F23 and F21 and F13 and F23 bonds, and 1 graph corresponding to 3 Fij bonds corresponding to F12, F13 and F23. In all, for a 3-particle system, there are 8 distinct graphs. One can therefore conclude that configurational integral Q over 3 particles, volume V and temperature T is sum of contribution of all distinct 3-particle graphs, that is, Q is equal to sum of contributions of all distinct 3-particle graphs. Furthermore, each one of these graphs can also be seen as made up of clusters. For example, number 1, figure 2 represents 3 1 clusters, number 2, figure 3 represents 3 possible 2 clusters, and number 3, figure 4 represents 4 possible 3 clusters. It is obvious from here that each of the L cluster corresponds to a L particle graph in which each of the L circles representing a particle is directly or indirectly linked with every other circle in it. For the purpose of accounting these clusters, let us represent by ml the number of L clusters in an n-particle graph. Then in the case of 3-particle graphs, if we represent m1 1 clusters M2 2 clusters and M3 3 clusters, then 3 particle graphs represented by figures 2 to 4 have different number of size clusters listed in table 1 below. For example, in figure 2, one graph, number of 1 clusters M1 is 3, number of 2 clusters M2 is 0, number of 3 clusters M3 again 0, and the set over these number of ML clusters, which is equal to a set M1, M2, M3 is 3, 0, 0, such that the sum over L is equal to 1 to 3 LML is equal to 3. For figure 3, 3 graphs, number of 1 clusters M1 is 1, number of 2 clusters M2 is 1, number of 3 clusters M3 is equal to 0, and the set ML is 1, 1, 0, such that sum over L is equal to 1 to 3 LML is again equal to 3. In figure 4, 4 graphs, number of 1 clusters M1 is 0, number of 2 clusters M2 is equal to 0, number of 3 clusters M3 is equal to 1, such that the set ML is 0, 0, 1, so that summation over L is equal to 1 to 3 LML once again turns out to be 3. It is worth noting that in a typical system, n is very large number with number of particles of the order of 10 is to the 23. It may have a very large number of n particle graphs larger than n. For example, we saw above that number of 3 particle graphs turned out to be 8 as shown in figure 2. Also, if we consider any one n particle graph, it may have a variety of clusters. For example, in the following graph for n is equal to 9 in figure 5 below, there are 2 1 clusters, 2 2 clusters and 1 3 cluster. The figure 5 9 particle graph depicts the corresponding integral, which is a product of 5 integrals with each integral representing a cluster of the 9 particle graph, which can be seen as a triple integral f1 to f1 over r1, r2 and r3, a single integral over r4, again a single integral over r6, multiplied by a double integral f5 over r5 and r7, multiplied by a double integral over f8 over r8 and r9. Also, there is a possible situation for a 9 particle graph when it cannot be split into a further product of clusters as shown below in figure 6. This corresponds to following integral, that is a 9-dimensional integral over f12, f23, f34, f56, f57, f47, f78, f89. This integral cannot be factorized into further subintegrals. To handle such a situation for an n-particle system, let us generalize and write Q is equal to sum of contributions of all distinct n-particle graphs and look for a suitable procedure to calculate the sum. Suppose for a particular n-particle graph, the number of 1 clusters is M1, the number of 2 clusters is M2 and so on, the number of L clusters is ML, then the set of numbers M1, M2 so on up to ML must satisfy the condition summation over L is equal to 1 to n, LML is equal to n, the number of particles, where ML is equal to 1, 2, 3 and so on up to n. We must keep in mind that the set ML represents a collection of graphs and not a particular graph. For example, in the case of 3 particle systems, 3, 0, 0, 0 set represented 1 graph, figure 2, 1, 0, 0 represented 3 graphs, figure 3, and 0, 0, 3 represented 4 graphs, figure 4. Let us denote the sum of the contribution of all these graphs by a sum S over the set ML, then Q will be equal to summation over the set ML SML, where the sum extends over all the members of the set ML satisfying the condition 23. Now let us try to construct this S as a function of the set ML. First step in constructing S as a function of set ML is to write down an arbitrary n-particle graph that has M1 1 clusters, M2 2 clusters, etc. That is, with the cluster set M1, M2 and so on with exactly n circles as shown below, which is an arbitrary one particle graph. Second step is to fill all these circles with numbers 1, 2 and so on up to n in a random order. Again, we may permute the numbering of all the n circles in figure 7, and that would lead to a distinct graph. If we add up all these possibilities, we obtain S over the set ML. Thus, we may write this set graphically as shown in figure 8 below. Let us understand the meaning of the graphical formula shown in figure 8. Each term inside the curly bracket contains the sum over L clusters. If each bracket is expanded in multinomial expansion, the summation over P will itself be a sum of large number of terms in which every term contains exactly n terms. The summation over P extends over all distinct ways of numbering these circles from 1 to n. Each graph is an integral whose value is independent of the way the circles are numbered. This integral is called Myers cluster integral and is defined as follows. BL as a function of Vt is equal to 1 upon L factorial lambda raised to power 3L minus 1 multiplied by B whole multiplied by sum of all possible L clusters, where normalization factor is so chosen to make BL Vt dimensionless, and in the limit V approaching infinity, VL as a function of V and T is a finite number. This is so because of the fact that the Meyer function Fij extends over a short range. In an L cluster, the result of the integration will be finite. Integration over the center of gravity of the cluster gives rise to a factor V, which then cancels out. And if we compare 13, the first few integrals can be written as known as cluster integrals. B1 is equal to 1 upon V sum of all possible 1 clusters, which is equal to 1 upon V integral over d cube R1, which is equal to 1. B2 is equal to 1 upon V sum of all possible 2 clusters, which is equal to 1 upon 2 factorial lambda raised to power 3 V multiplied by integral over f1 to d cube R1 d cube R2 is equal to 1 upon 2 lambda cube integral over f1 to d cube R1 d cube R2. B3 is equal to 1 upon V sum of all possible 3 clusters, which is equal to 1 upon 3 factorial lambda cube V integral over f1 to f23 plus f1 to f13 plus f13 f23 plus f1 to f13 f23 d cube R1 d cube R2 d cube R3, which is equal to 1 upon 3 factorial lambda cube V integral over 3 V f1 to f13 d cube R1 to d cube R13 plus V times f1 to f13 f23 d cube R1 d cube R13, which is equal to 1 upon 3 factorial lambda cube V integral over 3V f1 to f13 d cube R1 to d cube R13 plus V times f1 to f13 f23 d cube R1 to d cube R13 is equal to 2B2 square plus 1 upon 3 factorial lambda cube integral over f1 to f13 f23 d cube R1 to d cube R13. Therefore, in terms of cluster integrals, any term in S over a set ML can be represented as equal to 1 factorial into VB1 raised to power M1, 2 factorial into VB2 raised to power M2, 3 factorial into VB3 raised to power M3, and so on. Let us now see how to count the terms. To know how many terms are there in the sum over P, we first note that first there are n factorial permutations for n particle coordinates, and each of these permutations correspond to the same set ML. There are MLL clusters, and a permutation of these ML things doesn't lead to a new graph. The number of such permutations taking all clusters is the product M1 factorial, M2 factorial, m3 factorial and so on up to ml factorial, or a product over L ml factorial. Permuting all particles in one cluster among themselves leads to L factorial base, and in ml clusters of L particles this amounts to a total of L factorial raised to power ml base, which do not lead to new graphs. The number of permutations taking all clusters into account are therefore 1 factorial raised to power m1, 2 factorial raised to power m2, 3 factorial raised to power m3, 4 factorial raised to power m4, so on up to L factorial raised to power ml, which is nothing but a product over L factorial raised to power ml. Hence, the number of terms in the distribution summation over p are n factorial divided by product over L ml factorial multiplied by product over L factorial raised to power ml. Therefore, the function S over the set ml is equal to n factorial over the product over L ml factorial multiplied by product over L factorial raised to power ml whole multiplied by product over L is equal to 1 to n over L factorial lambda raised to power 3L minus 1 VBL whole raised to power ml, which is equal to n factorial product over L is equal to 1 to n lambda raised to power 3L minus 1 VBL raised to power ml divided by ml factorial, which can be rearranged is equal to n factorial multiplied by the product over L is equal to 1 to n lambda raised to power 3L ml multiplied by 1 upon ml factorial multiplied by VVL upon lambda cube raised to power ml, which is equal to n factorial lambda raised to power 3 summation over L LML multiplied by product over L is equal to 1 to n 1 upon m factorial multiplied by VBL upon lambda raised to power 3 raised to power ml, which is equal to n factorial multiplied by lambda raised to power 3n multiplied by the product over L is equal to 1 to n 1 upon ml factorial multiplied by VVL upon lambda cube raised to power ml. Using 24th, we get q as a function of n, v and t is equal to summation over the set ml n factorial lambda raised to power 3n multiplied by product over L is equal to 1 to n 1 upon ml factorial VBL upon lambda cube raised to power ml. Therefore, from 7th we get z, the total partition function, is equal to 1 upon n factorial lambda raised to power 3n multiplied by q times n v t is equal to summation over the set ml over the product L is equal to 1 to n 1 upon ml factorial multiplied by VVL upon lambda cube raised to power ml. It is a canonical partition function and has a severe restriction of summation over L LML is equal to n, which must be obeyed by every subset over ML. To overcome this, we may choose the grand partition function of the system capital Xi over the chemical potential mu, volume V and temperature T is equal to summation over n is equal to 0 to infinity e raised to power mu n upon kBT multiplied by the canonical partition function z as a function of n, v and t, or capital Xi as a function of mu, v and t is equal to summation over m1, m2 and so on from 0 to infinity e raised to power mu summation over L LML divided by kBT into the canonical partition function z n v t is equal to summation over m1, m2 and so on from 0 to infinity product from 1 to infinity over L e raised to power mu L ml upon kBT multiplied by the canonical partition function z, which is a function of n, v and t, or capital Xi as a function of mu, v and t, also called the grand partition function, is equal to summation over m1, m2 and so on from 0 to infinity multiplied by the product over L from 1 to infinity 1 upon ml factorial e raised to power mu L upon kBT VBL upon lambda cube raised to power ml. If we define e raised to power mu upon kBT is equal to f, the fugacity, the grand partition function capital Xi over a function of fugacity f, volume V and temperature T is equal to summation over m1, m2 and so on from 0 to infinity. Product over L is equal to 1 to infinity 1 upon ml factorial fl vbl upon lambda cube raised to power ml is equal to product over L is equal to 1 to infinity summation over ml is equal to 0 to infinity 1 upon ml factorial f raised to power L vbl upon lambda cube raised to power ml is equal to product over L is equal to 1 to infinity e raised to power f raised to power L vbl lambda cube is equal to e raised to power summation over L is equal to 1 to infinity f multiplied by L vbl upon lambda cube, or log of the grand partition function capital Xi as a function of fugacity, volume V and temperature T is equal to V upon lambda cube summation over L is equal to 1 to infinity f raised to power L bl. Recalling that pressure P is equal to kBT as a partial derivative of log of the grand partition function with respect to volume, P upon kBT is equal to 1 upon lambda cube summation over L is equal to 1 to infinity f raised to power L bl. Further recalling that the number of particles n is equal to fugacity times partial derivative of log of the grand partition function with respect to f, n upon V is equal to 1 upon lambda cube summation over L is equal to 1 to infinity over L f raised to power L bl. Equation 39 and 40 constitute parametric form of the equation of state, also known as cluster expansion of the equation of state. Eliminating fugacity f gives the equation of state. Connecting virial expansion of equation of state and cluster expansion of equation of state. From equation 40, it is clear that fugacity f depends only on the parameter n lambda raised to power 3 divided by V. Therefore, there exists a series expansion which we can write as fugacity is equal to summation over L is equal to 1 to infinity Cl multiplied by lambda raised to power 3 times the number of particles n divided by V whole raised to power L is equal to summation over L is equal to 1 to infinity Cl multiplied by lambda raised to power 3 upon V upon n raised to power L is equal to summation over L is equal to 1 to infinity Cl lambda raised to power 3 divided by nu raised to power L, where nu is equal to V upon n is the volume per particle in the system and Cl depends only on Bl, the cluster integrals. If we insert 41 in 39, we get, after ordering the powers of lambda cube by nu, a series expansion of equation of state, that is, P upon kBT is equal to 1 upon lambda cube summation over L is equal to 1 to infinity f raised to power L bl is equal to summation over L is equal to 1 to infinity 1 upon nu into Al as a function of t multiplied by lambda cube upon nu raised to power L minus 1, or P nu upon kBT is equal to summation over L is equal to 1 to infinity Al as a function of t multiplied by lambda cube upon nu raised to power L minus 1, where Alt is known as the Lth virial coefficient. Our aim is to determine Als in terms of Bl. Since from 40 we know that lambda cube upon nu is equal to summation over L is equal to 1 to infinity Lfl raised to power L Bl, and from 39 and 40 we know that P nu upon kBT is equal to summation over L is equal to 1 to infinity over f raised to power L Bl divided by summation over L is equal to 1 to infinity over L f raised to power L Bl. Substituting 44 on the right hand side of 43 and equating this to 45, we get summation over L is equal to 1 to infinity Al as a function of t multiplied by summation over m is equal to 1 to infinity m times f raised to power m bm raised to power L minus 1 is equal to summation over L is equal to 1 to infinity f raised to power L Bl divided by summation over L is equal to 1 to infinity L f raised to power L Bl. Or summation over L is equal to 1 to infinity f raised to power L BL is equal to summation over L is equal to 1 to infinity L f raised to power L BL multiplied by summation over L is equal to 1 to infinity AL as a function of t multiplied by summation over m is equal to 1 to infinity m f raised to power m bm raised to power L minus 1. Expanding the brackets on the two sides, we obtain b1f plus b2f raised to power 2 plus b3f raised to power 3 is equal to b1f plus 2b2f raised to power 2 plus 3b3f raised to power 3 plus so on, multiplied by a1 plus a2 into b1f plus 2b2f raised to power 2 plus 3b3f raised to power 3 plus so on, plus a3 into b1f plus 2b2f raised to power 2 plus 3b3f raised to power 3 plus so on whole square plus so on. For the two sides to be equal in 48, coefficients of the equal powers of f on the two sides must be equal. Therefore, we obtain b1 is equal to a1 b1 or a1 is equal to 1, b2 is equal to a2 b1 square plus 2a1 b2. Also we know from 26 that b1 is equal to 1, therefore a2 is equal to minus b2, which is equal to minus 1 upon 2 raised to power lambda cube integral over f1 to d cube r1 d cube r2 is equal to minus 2 pi upon lambda cube r square fr dr is equal to minus 2 pi upon lambda cube r square e raised to power mu r upon kbt minus 1 into dr. b3 is equal to 3a1 b3 plus 4a2 b2 b1 plus a3 b1 square. Also we know from 26 b1 is equal to 1, and from 28 therefore a3 is equal to minus 2b3 plus 4b2 square is equal to minus 2 multiplied by b3 minus 2b2 whole square, which is equal to minus 1 upon 3 lambda cube integral over f12 f13 f23 d cube r12 d cube r13 and so on. From equation 51, it is interesting to observe that the third virial coefficient is determined solely by the 3 cluster. This points to a possibility that the higher order virial coefficients can solely be determined only by a special class of L cluster graphs, where each pair of points can be connected by at least 2 independent non-intersecting paths. Such L cluster graphs are called irreducible graphs. This is essentially the linked cluster expansion, which states that in thermodynamic limit, some should be carried over only irreducible cluster graphs. A graph is said to be reducible if it can be split into two parts by cutting one bond. The linked cluster results take the form, for example, for the grand canonical potential as equation 38 log of the grand partition function xi is equal to sum over linked clusters counting factor into cluster integral. The counting factor takes into account topologically similar diagrams that give the same integral and numerical factors depending on the order of the term. It is also worth mentioning that at this stage we can again guess that only linked clusters occur in the thermodynamic quantities, since other terms do not fulfill the criteria of extensivity with respect to volume. Calculation of B2 as a function of t and B3 as a function of t. In the beginning of this module, we wrote equation of state of a real gas, equation 1, called the Virial expansion, namely P upon kBt is equal to small n, the number density, plus B2t multiplied by number density square plus B3t multiplied by number density cube plus so on. It can also be written in terms of nu, which is equal to 1 upon n, which is equal to the ratio of V upon n, that is the volume occupied by each atom or molecule. Therefore, P nu upon kBt is equal to 1 plus b2t into 1 upon nu plus b3t into 1 upon nu whole square. Comparing 54 and 53 gives b2t is equal to a2t lambda raised to power 3 is equal to minus 2 pi upon lambda cube into lambda cube integral over r square e raised to power minus ur upon kbt minus 1 d cube r is equal to minus 2 pi integral over r square e raised to power ur upon kbt minus 1 into dr, and b3t is equal to a3t lambda cube raised to power 2, which is equal to minus 1 upon 3 over f12, f13, f23 d cube r12 d cube r13. It needs to be noted here that this expansion is valid in the case of dilute gases only. Limitations of cluster expansion. Limitations of cluster expansion. Cluster expansion has number of limitations. First, cluster expansion works only when density is small. In the high density limit, that is in the case of liquids, size of the clusters become very large as if every particle is a part of this cluster, which makes nth order term a very important term and cannot be neglected. The main aim of the Meyer cluster expansion was to provide a theoretical basis for condensation, and it could not explain the existence of condensation point. It failed to provide an equation of state which correctly describes a phase transition. In this module, students, we have learned that Virial equation of state was proposed by Thiessen and Kemling-Owens as an infinite power series of number density with coefficients of different power terms described as a Virial coefficient, namely P upon Boltzmann constant Kb multiplied by T is equal to n plus B2 as a function of T n square plus B3 as a function of T multiplied by n cube plus so on, where B2 and B3 are Virial coefficients. We learned that van der Waals phenomenological equation of state can be expanded as a power series in number density, which can be written as P upon Boltzmann constant Kb multiplied by T is equal to n plus B minus A n square plus B square by 2 n cube plus so on. That canonical partition function for a non-ideal gas for a typical interparticle potential U can be written as Z as a function of n, V and T is equal to 1 upon n factorial lambda raised to power 3n integral over product over I less than j e raised to power minus beta uij d raised to power 3n r, which is equal to 1 upon n factorial lambda raised to power 3n q times q as a function of n, v and t, which reduces to ideal gas partition function in the absence of interparticle potential, as z raised to power 0 as a function of n, v and t is equal to 1 upon n factorial lambda raised to power 3n integral over d raised to power 3n r is equal to v raised to power n upon n factorial lambda raised to power 3n, where q n v t is also called configurational partition function. That Meyer function Fij is equal to e raised to power minus beta uij minus 1 because of its typical r dependence compared to that of e raised to power minus beta uij is the most appropriate function to choose to have a convergent series expansion. We learned that configurational integral can be expanded in terms of Meyer functions as q as a function of n, v and t is equal to a multidimensional integral over r1, r2, r3, rn for the function 1 plus summation over I less than j, Fij summation over I and k, I less than j and k less than l, fij, fkl plus so on. We learned that there is an interesting graphical way to represent the n-particle configurational integral expanded in terms of Meyer function as n-particle graphs, leading to the notion of clustering, which facilitates the calculation of n-particle configurational partition function. We learned that the configurational particle function q as a function of n, v and t is equal to sum of contributions of all distinct n-particle graphs, which can be represented as a sum over the set ML of the function SML, where ML is a set over all L cluster graphs such that summation over L ML multiplied by L is equal to the number of particles n. Symbolically, this function S can be represented by a sum of graphs as shown here, where each graph is an integral whose value is independent of the way the circles are numbered. This integral is called Meyer's cluster integral. That Meyer's cluster integral is defined as BL as a function of the product of volume and temperature is equal to 1 upon L factorial lambda raised to power 3 times L minus 1 multiplied by V whole multiplied by sum of all possible L clusters with B1 is equal to 1 upon V sum of all possible 1 clusters is equal to 1 upon V integral of d cube R1 is equal to 1, B2 is equal to 1 upon B sum of all possible 2 clusters is equal to 1 upon 2 factorial lambda cube into V integral of F1 to d cube R1 d cube R2 is equal to 1 upon 2 lambda cube integral over F1 to d cube R1 2. B3 is equal to 1 upon V sum of all possible 3 clusters is equal to 1 upon 3 factorial lambda cube times V integral of F1 to F23 plus F1 to F13 plus F13 F23 plus F1 to F13 F23 integrated over R1 R2 R3, which is equal to 2b2 square plus 1 upon 3 factorial lambda cube integral over F1 to F13 F23 d cube R1 to d cube R13. We learned that canonical partition function in terms of cluster integrals can be obtained as z as a function of nvt is equal to 1 upon n factorial lambda raised to power 3n multiplied by the configurational partition function q as a function of n, v and t is equal to summation over the set ML of the function product over L is equal to 1 to n 1 upon ml factorial multiplied by VBL divided by lambda cube whole raised to power ml. We learned that to overcome the severe restriction of the constraint summation over L, LML is equal to n on the canonical partition function, which must be obeyed by every subset of ML, one may choose the grand partition function of the system as xi, which is a function of chemical potential mu, volume V and temperature T is equal to summation over n is equal to 0 to infinity e raised to power mu n upon kBT multiplied by the canonical partition function z as a function of n, v and t. We learned that the parametric form of the equation of state in terms of cluster integrals with fugacity as a dispensable parameter can be written as a set of following two equations, namely P upon kBT is equal to 1 upon lambda cube summation over L is equal to 1 to infinity f raised to power L multiplied by BL and n upon V is equal to 1 upon lambda cube summation over L is equal to 1 to infinity over L f raised to power L BL. Virial expansion of equation of state can be obtained as P nu over kBt is equal to summation over L is equal to 1 to infinity AL as a function of t lambda q upon V raised to power L minus 1, where ALT is the Lth virial coefficient. The first three of these can be obtained for systems with a given interparticle potential as A1 is equal to 1, A2 is equal to minus 1 upon 2 lambda cube integral over F12 d cube R1 d cube R2, which can be written as equal to minus 2 pi upon lambda cube integral over r square fr dr, which is equal to minus 2 pi by lambda cube integral over r square e raised to power minus ur upon kbt minus 1 dr, and A3 is equal to minus 2b3 plus 4 times b2 square is equal to minus 2 times b3 minus 2b2 square is equal to minus 1 upon 3 lambda cube integral of F12, F13, F23 multiplied by d cube R12, d cube R13. We learned that Meyer's cluster expansion works only for low density gases and fails to explain condensation phenomena in gases. Thank you.